Hi. I had this sort of question about velocity curves, question about how they looked. I decided to put together a sort of demonstration of velocity distributions in Mathematica, trying to show the difference between rotational rigidity, uniform density, and point mass. Here's what rotational rigidity looks like. Basically, what we have is an initial random distribution of particles rotating around a point. There's no scattering of the particles as they go around. This is essentially what you have when you have the rotation of a solid. But there's more than that. You know when you look up at the moon and you see the same face every day and every night? That's because the moon is rotationally rigid with the center of gravity of the Earth-Moon system. But what about the solar system? The solar system is governed by an equation that says that the centripetal force is equal to the gravitational force. The centripetal force is known given the radial velocity and the radius. The gravitational force is also known given the mass of the Sun, the radius, and the universal gravitational constant. There's one other thing you need to figure out: the force, the mass of the object attracted by the force. But for our purposes, that mass will cancel out of the equations, and we can just say mass times acceleration equals the force divided by that mass. And so these would ordinarily include an extra little m and a little m there too. But since that little m divided out, it's not a big deal. We could also imagine a system where the mass wasn't all concentrated at the very center. In a system with uniform density, sigma, we would replace the value of m here, with a quantity that varied with the radius, sigma pi r squared. And when we do that, we get a velocity distribution that drops off with the square root of the radius, actually an angular velocity distribution, that drops off with the square root of the radius instead of the square root of the cube of the radius. And that kind of looks like this. Okay, if you watch this one, you'll see the tails from the corners form quite a bit more slowly. While that's going on, I'll show you below the basic design of the Mathematica code. First, I created a square made of 2,000 dots, simply using a random number between -1 and 1 in the x-coordinate, random real number between 0 and 1 multiplied by 2 and then subtracting 1. So that gives us a random number between -1 in the x-coordinate and the same in the y-coordinate. That forms the initial square. So next, we established an angular velocity here by first converting the Cartesian coordinates into polar coordinates. Let's see, r equals, so r and theta are given, oh wait, did we do it back here? I crossed that out, but I shouldn't have, because it took that list over here and turned it into another list. I just misnamed it. Yes, it should have been RT list instead of, no, it shouldn't have been. Oh, here we are. The original list had polar coordinates because I said here theta equals arctangent of x, y, and r equals square root of x squared plus y squared. Now we put an angular velocity in play by multiplying by an angular velocity of either the square root of r to the first, or for uniform distribution rotation, or the square root of r cubed for, and I can change that here, r cubed for rotation around a point mass. Or, of course, I can put in r equals, or velocity of r to the 0 for rigid rotation. Then, just for fun, I allowed for negative values of the power so we could see negative velocity distributions, so that the velocity distribution that is faster on the outside. I think that's all I have to say.